Hello again. Today we are going to continue to discuss acids and bases. Last time we talked about pH and pOH, and from pH and pOH we can determine concentrations of hydronium ions and hydroxide ions. And today we're going to apply some of those ideas in combination with equilibrium. And we're going to determine the pH of a weak acid, for instance. So if you are a little rusty on equilibrium and how to do ice tables, I would go back and go over chapter 15 again. We are going to go over a couple of practice problems, though. Okay, so there are two sources of hydronium ions in an aqueous solution of a strong or weak acid. So remember that water can react with itself to produce hydronium ions and hydroxide ions. So if you do add an acid to water, you'll also end up with hydronium ions and the conjugate base, but there are already some hydronium ions from the water itself. It's a really small amount. Remember that the concentration is 1 × 10⁻⁷ moles per liter. So it might not have that much of an effect on the overall concentration of hydronium ions in solution, but just keep in mind that there are two sources of hydronium ions. For a strong acid, the contribution of the water to the total hydronium ion concentration is negligible. So in that instance, we can assume that the concentration of the strong acid is equal to the concentration of the hydronium ions. And we don't have to take into account that really small amount of hydronium ions that are produced from the autoionization of water. For a weak acid, finding the hydronium ion concentration is more complicated, and that's due to the fact that the acid undergoes only partial ionization. So the concentration of hydronium ions from water could contribute to the overall concentration of hydronium ions in a weak acid solution. So how do we find the pH of a weak acid? First, we're going to write the equation for the acid, and then we're going to use that equation as a guide to prepare the ice table. So step 1 is really to write the equation for the acid in water. And then 2, we're going to complete the ice table based on given information. And we also want to keep in mind any reaction stoichiometry. So for instance, if the acid reacts in a 2-to-1 ratio with water, then we want to take that into account when we're considering any changes that are occurring in solution. And then 3, substitute the expressions for equilibrium concentrations into the expression for K. And then 4, determine the concentration of hydronium ions from the calculated value of X, which X is usually equal to the concentration of hydronium ions. And then we would calculate the pH as necessary. And then number 5, always check your answer. Make sure that your answer makes sense. Okay, so let's do a practice problem. It's always nice to have these steps handy, but of course, actually doing a problem and working through it is probably the best way to learn the material. So this example comes from your textbook. So if you want to follow along with your textbook, you can. And the example is find the concentration of hydronium ions for a 0.1 molar cyanic acid solution. Okay, so again, remember the first step is to write out the equation or the reaction equation. So here we're going to write out cyanic acid and water. Now, because cyanic acid is an acid, it's going to lose its hydrogen, and water is going to act as the base. So it's going to grab onto that hydrogen. So our products will be the cyanide ion and the hydronium ion. Okay, now the next step is to write out the ice table using the balanced chemical equation. So I'll do that in a different color. Remember that when we're writing ice tables, we're not going to include any pure liquids or pure solids because their concentrations don't change. So we're only going to include HCN. And then I'm going to draw a line here to kind of separate the reactants from the products. And then the products we'll write next to that. And then, of course, we're going to determine the initial concentrations for each, which is I. Then we're going to determine the change in concentration during the reaction, C. And then finally, we're going to determine the equilibrium expressions for each concentration, E. So we were told that the initial concentration of cyanic acid is 0.1 moles per liter. So we'll write that for initial. And then in terms of the products, we haven't started the reaction yet. We're just at the initial point. So we shouldn't have any cyanide ions. But remember, we do have a very, very small amount of hydronium ions just from the natural auto-ionization of water. However, it's so minimal that we're just going to say that the initial concentration of hydronium ions is approximately 0. Now we have to take into account any changes that might occur, and we don't know what that change is yet, so we're just going to label the change with an X. And if we lose anything, so if, for instance, a reactant starts reacting, it's going to slowly disappear. So we would want to write negative X for that change. And then for the products, those are going to slowly start appearing in solution as the reaction continues. So we're going to write plus X for each product. And here, everything reacted in a 1-to-1 ratio, so we don't have to take into account stoichiometry. However, remember that if you do have, let's say, a 2-to-1 ratio between a reactant and a product, you do want to take that into account in your change. Now for equilibrium, we're just going to add together the first two columns, or sorry, the first two rows for each column. So for HCN, the equilibrium concentration would equal 0.1 minus X. For cyanide, it's just X, and for the hydronium ions, it's also just X. Okay, now the next thing we want to do is plug each of these equilibrium expressions into the expression for K. So for this particular reaction, we're going to consider the acid ionization constant, Ka. And remember, we write the products, the concentration of the products in the numerator. And then we write the concentration of the reactants in the denominator. But in this case, water is not included since it is a pure liquid. Okay, now we do need to determine what the acid ionization constant is for cyanic acid. So let's actually go to that table from your textbook, table 16.5. And kind of towards the bottom is cyanic acid, which they're actually calling it hydrocyanic acid. And the Ka value is 4.9 times 10 to the negative 10th. All right, so we're going to plug that into our expression for Ka. So let's rewrite that expression. And now we know that Ka is equal to 4.9 times 10 to the negative 10th. And then we can also plug in our equilibrium concentrations for each. So in the numerator, we would have x squared, because both Cn and H3O plus are equal to x. And then in the denominator, we would write 0.1 minus x. Now you might recall from chapter 15 that we could make an assumption that x is really small as long as the value of k is really, really small. So on the order of 10 to the negative 5th or less. So in this case, we have something that's on the order of 10 to the negative 10th. So we can definitely assume that x is small here. So that means that we can just ignore that change in x in the denominator, and then we can solve for x more easily. So let's multiply 0.1 by our value of Ka, and then we're just setting that equal to x squared. So we should get that x squared is equal to 4.9 times 10 to the negative 11th. And then we're going to take the square root of both sides so that we can figure out what x is equal to. And after we plug that into our calculator, we should find that x is equal to 7 times 10 to the negative 6th. And remember that x is also equal to the concentration of hydronium ions in solution. But we should always check our answer first and make sure that it is valid. We also should check our assumption. So let's check. So first let's check our assumption that x is small. And to do that, we're going to take the concentration of hydronium ions at equilibrium and then divide that by the concentration of the acid at its initial point. And then we multiply by 100. And if the percentage here is less than 5%, then that means that our assumption is valid. So if we plug in 7 times 10 to the negative 6th over 0.1 times 100, the percentage comes out as 0.007. So that means that our assumption that x is small is valid. Now remember, if our assumption was not valid, then we had to use the quadratic formula. So that could pop up here and there. But in this case, we don't have to worry about that. Now, let's also check that our value of x makes sense for the Ka value. So let's try calculating Ka based on the value of x. So we said that Ka is equal to x squared over 0.1 minus x. And if we plug in 7 times 10 to the negative 6th and square it, and then divide that by 0.1 minus 7 times 10 to the negative 6th, we do end up getting the same value of K that we found in our table. So again, remember to always check your answer. Does your answer make sense? Do you actually get the same value back? And if you're making any assumptions about x, make sure to double check that your assumption is valid. All right. Let's do another example problem. In this problem, we're told that a 0.1 molar weak acid, HA, has a pH of 4.25. Find Ka for the acid. So we don't know what this acid is, so we can't look up its Ka value in a table. So instead, we're going to have to use the given information to determine what the Ka value is. So let's start by writing out the equation for HA. Aqueous. So we have our acid, and water is the base. And that means that the acid is going to give a hydrogen to water. And we end up with A minus, the conjugate base, and H3O plus is the conjugate acid. And then we're going to write out our ice table. And I'm going to separate the products from the reactant again. And we were told that the initial concentration of the acid was 0.1. And then we can assume that the initial concentration of A minus is 0. And then the concentration of the hydronium ions is approximately 0. Now, normally we would go through and similar to before, we would say, okay, the change for HA is minus X, the change for A is plus X, and then the change for the hydroniums ions is plus X. But what's great is that we're told the pH of our solution. So we can figure out the concentration of hydronium ions at equilibrium, which is X. So X, which is equal to the concentration of hydronium ions, can be solved for by using the inverse log equation that we saw last time. So we had said that the concentration of hydronium ions is equal to 10 to the negative pH. So in this case, that's 10 to the negative 4.25. And if we plug that in, we end up with a value of 5.6 times 10 to the negative fifth. So that means that the change in our acid is minus 5.6 times 10 to the negative fifth. And then the change in A is plus 5.6 times 10 to the negative fifth. And that's the same for the hydronium ions. So at equilibrium, the concentration of HA is 0.1 minus 5.6 times 10 to the negative fifth. And that's actually still equal to about 0.1. So the concentration of the initial acid did not change very much. And again, remember, this is a weak acid, so that kind of makes sense, right? Weak acids don't produce very many hydronium ions. And then the equilibrium concentration for the conjugate base is just 5.6 times 10 to the negative fifth. And then that would be the same for the hydronium ion, which we already calculated. All right. Now, the next thing we have to do is calculate Ka for the acid. So let's write out what the expression for Ka is. And now we just have to plug in the values for each at equilibrium. So we said that the concentration of A at equilibrium is 5.6 times 10 to the negative fifth. And then for the hydronium ion, we have the same value. And then we're going to divide that by the initial concentration, or the concentration of HA at equilibrium, which was approximately the same as the initial concentration. So that was 0.100. So once we plug all of that in, you should get a value of 3.1 times 10 to the negative 8th. So double check in your calculator that you got the same thing. And again, you always want to check that your answer makes sense. So we do have a small value of Ka, which means that we have a weak acid. But additionally, you might want to go back and make sure that you get an appropriate value of pH for the concentration of, or from the Ka value here. Okay, so let's work on a worksheet problem, problem 4. And in problem 4, we're going to determine the concentration of hydronium ions. And from there, we'll be able to determine the pH. And this is for a 0.2 molar solution of formic acid. Now, one thing that's not listed here is the Ka value for formic acid. So I'll give that to you here. Although I believe that is listed in your worksheet. But the Ka value for formic acid is 1.8 times 10 to the negative fourth. Now, if you want to attempt this problem on your own, this problem is more similar to the first example problem we did. So if you want to do this on your own first, feel free to pause the video, and then you can restart the video and see if we got the same answer. Okay, so let's go over this problem together. Remember that the first thing you should do is write out the equation, or the reaction equation. So we're told that formic acid is HCHO2, and that's going to react with water. And because formic acid is an acid, that means water is going to act as a base and take a hydrogen from the acid. Or I guess accept a hydrogen from the acid. And then in the products, we'll end up with CHO2 minus, because formic acid has lost a hydrogen ion, so it's now negative. And then we'll also end up with the hydronium ion as our other product. So we have our conjugate base and our conjugate acid. Now we can use that equation to help us form our ice table. And again, I'm just going to separate the reactant from the products. Now, starting with the initial row, we were told that the initial concentration of formic acid is 0.2 moles per liter. And as before, we can assume that we don't have any of the product. And we have approximately 0 hydronium ions. Now for the change, because the reaction is occurring towards the products, we're going to lose some amount of the reactant. We're going to gain some amount of each product. And then in the equilibrium step, we're just going to add together the first two rows for each. So the equilibrium expression or concentration for the reactant is 0.2 minus X. And then for each of the products, the equilibrium concentration is X. So now the next step is to write out the expression for the acid ionization constant. So let's do that on a separate slide. So again, we have the concentration of the products in the numerator, and they're multiplied by each other. And then in the denominator, we have the concentration of the reactant. And all of these concentrations are at equilibrium. So now we just plug in the values that we have. I told you earlier that the Ka value for formic acid is 1.8 times 10 to the negative fourth. And then from our ice table, we saw that the concentration for each of the products is X. So we'd end up with X squared in the numerator. And then in the denominator, we would write in the equilibrium expression for the acid, which is 0.2 minus X. Now, in this case, our value of Ka is a little on the high side. So we're still going to assume that X is small, and we'll see if it works out, but we might end up having to use the quadratic formula. So let's start by making an assumption that X is small, and then we'll just make sure to check our assumption before we assume that we're correct. Okay, so let's ignore that change in X on the denominator. And that means we're going to multiply the value of Ka by 0.2. And then we set that equal to X squared. And we just take the square root of both sides to find X. So X should equal 0.006. And remember, this is also equal to the concentration of hydronium ions. Now, remember, we should check that this is a valid assumption. So we're going to take our equilibrium concentration of the hydronium ions, and we're going to divide that by the initial concentration of the acid, and then multiply that by 100. So we have 0.006 divided by 0.2 times 100. And remember that for the assumption to be valid, the percentage should be 5 or less. Now when we calculate this, we get a value of 3%. So that means that our assumption is correct. So sometimes if your Ka value is slightly greater than 10 to the negative fifth, you can still assume X is small, but it is kind of on the border of the assumption working out. So in some cases, you might still have to use the quadratic formula. All right, so now that we know that our assumption is valid, we can now calculate the pH of this solution. So remember that pH is equal to the negative log of the concentration of hydronium ions. So we're going to plug in the concentration that we calculated, which is 0.006. And after plugging this in, we should get a pH value of 2.22. All right. So hopefully that helps a little bit and refreshes your memory on equilibrium problems and using ice tables. Again, if you're a little bit rusty or feeling a little bit unsure about equilibrium problems, especially using ice tables, go back to chapter 15, and I recommend working through some of the practice problems in chapter 15, just to make sure that you feel comfortable with the material. Okay, we're going to stop lecture there today, and in the next video, we'll talk about percent ionization of acids.